Okay, guys, welcome back. So we finished the wave nature of light previously, and now we are going to go a little bit deeper into what light actually is. And again, that's a bit of a controversial topic even within physics because there's a sort of quantum interpretation of light and the wave interpretation of light. But again, we're not doing modern physics, or at least not quantum physics. So we're still sticking with waves and treating light as a wave. But now we're going to get a little bit deeper into what does it mean for light to be a wave? What's actually What's actually oscillating here? So here are the goals in this chapter. So we're going to understand what electromagnetic waves are, what the speed of light is, and the electromagnetic spectrum. So the different components, the different frequencies, what they mean, how they're used, stuff like that. We're also going to mathematically represent these waves. So we call these characterizing sinusoidal waves. We will not be doing energy. We will not have time to do energy in the same way that we didn't do magnetic energy. And then after all of this is taught, hopefully students are able to then describe the nature of light, how we can create light, what creates light fundamentally. And we've already sort of done these previously in a previous chapter. Okay, so first things first, what is light? Well, light is simply, I'll come back to that in a second, light is simply an oscillating electro and magnetic field. That's it, that's what it is. We've been talking about light as a wave. What is physically oscillating? What is the wave? The wave is physically an electric field that is oscillating sinusoidally, and the B field that is oscillating in phase sinusoidally. That is physically what a light wave is. Oscillating electro and magnetic field. Okay, I will come back to this briefly, well, not briefly, I will come back to this shortly and explain why this is what light is and why there's an electric and a magnetic field together. But before we do that, let's get into a little bit of characteristics of this. So we use the right-hand rule to determine direction of propagation. So we use your right hand, put your fingernails in the direction of the electric field. So I guess if you're looking at your tablet or your computer screen, put your fingernails straight up on your right hand. And then curl your fingernails in the direction of B. Ooh, it didn't, oh, it doesn't want to change color, of course. Curl your fingernails in the direction of B. And then your thumb will point in the direction of propagation, the direction of the light ray. So that's how you use the right-hand rule to determine the relationship between the electric field, the magnetic field, and the direction of propagation. Now, the intensity of the electric field compared to that of the magnetic field is scaled by the speed of light. Another way to write this is that the speed, all right, I can't, hold on, let me minimize and resume. Okay, can I change color now? Yes, I can. Another way to write this is that the speed of light is actually defined to be the magnitude of the electric field divided by the magnitude of the B field. And the ratio of those two fields gives you the speed of light. Now, you might be asking yourself, well, is that just is that number just is what it is? You know, it's just, where did that come from? Is that just a fact of nature, or did that come from, is there a better way to understand that? There is, in fact, a better way to understand that. And you can actually use Maxwell's equations to solve for the speed of an electromagnetic wave. And it's a little bit confusing because you need some vector calculus and curls and divergences, and that is completely beyond the scope of this course. So unfortunately for this very small thing, it's going to have to be a proof by trust me. But you can use Maxwell's equations to solve for the speed of light, and it just so happens you end up getting the speed of light to be 1 over root mu naught epsilon naught. And we know what these are separately. We know mu is 4 pi times 10 to the minus 7, I believe. And epsilon naught was, I'm really testing my memory now, 8 point, I want to say 678 or something like that, times 10 to the minus 9. I don't know. I'd have to look up epsilon naught off the top of my head. If anyone live at the moment knows what the value of epsilon naught off the top of their head, please throw it into the chat. Anyway, whatever those two happen to be, you could look them up as constants. If you plug them in and you multiply them together, take the square root, and then take the reciprocal, they will end up being 2.999 times 10 to the 8, which is effectively 3 times 10 to the 8, which is what we call the speed of light in a vacuum. And this equation actually explains why the speed of light in different materials is different. So, with geometric optics, we talked about the index of refraction, and we talked about, the speed in glass is different than air, the speed of water is different than air. So the index of refraction for water is 1.33 because it's slower in water compared to air. Now there's actually a way in which we can mathematically derive or predict what the index of refraction of the material is. Because if you recall, the index of refraction of the material was N equals C over V, where C is the speed of light in a vacuum divided by V. The V is the speed of light in that material. And before, we would have to measure that empirically and then reverse engineer what the index of refraction is. However, now we can say this is simply 1 over, and the speed of light we know is 1 over root mu epsilon, and that's a compound fraction, so we can kind of flip it up and simplify this a little bit. So we can now calculate the index of refraction of a material without doing an experiment. All we need to know is what the permittivity of free space is and the permissivity, or not free space, the permittivity and permissivity of that material is. And as long as we have that, we don't need to do any experiments. We can inherently predict what the index of refraction of that material will be. Okay, here I've already explained the right-hand rule, but in the event that, I don't know, you couldn't picture it without a diagram, here's a diagram. So, first you point your fingernails in the direction of the E field, wherever the E field happens to be. You curl your fingernails around in the direction of the B field. In this case, that's the positive Z direction. And then your thumb points in the direction of propagation. So the light ray is traveling in the X direction here. Okay. So here's the electromagnetic spectrum. So visible light is, as you can see, a very, very small sliver of the electromagnetic spectrum. So we can talk about it either in terms of wavelength or frequencies. Most physicists usually talk about the electromagnetic spectrum in frequencies, but I'll try to do both for you. So wavelengths, well, wavelengths are measured in meters, lambda, and you can have wavelength 0, meaning you don't really have a wave, or you can have a wavelength that's really large. So some context for you. Well, radio waves and TV waves, radio waves like literally like in your car when they broadcast a radio station, those wavelengths are on the order of magnitude of meters. Now, your car, the length of your car is, I don't know, probably about 5 meters, 5 or 6 meters, I would say, from bumper to bumper. And radio waves are on the order of magnitude between 1 meter and 10 meters, depending exactly on AM, FM radio, and all this other stuff. So one cycle, one wavelength of radio wave is on the order of magnitude of the length of your car, which is pretty cool. You know, most people think of radio waves as like, you know, something that's so small that, you know, you can't ever see. That's not true. I mean, they're invisible, obviously, because your eyes can't see them, but they're huge. Like, I mean, most people are 5 or 6 feet tall, somewhere in that range. You know, just over a meter and a half. That is on the order of magnitude of a radio wave. Your height is roughly the height of one lambda, one wavelength of a radio wave. That's pretty cool, I think, just to think about. In terms of frequencies, now don't forget this equation, V equals F lambda. So this is going to be the speed, which is a constant, which means if lambda is really big, then frequency is really small, and sort of vice versa. So because the product has to be a constant. So here, if the wavelength is relatively fairly large, so the frequency is going to be relatively fairly small. I know 10 to the 8 doesn't seem small, but it is relatively small compared to how the other frequencies will compare. So the low end of the frequency spectrum is 10 to the 8, which is in and around the megahertz region, So microwaves is what comes next. And you know, your microwave oven, literally it's called microwave for a reason. Scientists are not the most creative people in this sense. Your microwave oven produces microwave electromagnetic radiation, and it's slightly more intense, it's slightly more deadly, sort of, in the sense that it can jiggle water molecules. So the premise of a microwave is that every molecule of everything has a natural frequency that it oscillates at. You know this from chemistry. That's how we measure temperature. Temperature is the measure of average kinetic energy of the molecules. So everything is sort of vibrating back and forth. And if you picture that sort of vibration like someone on a swing, maybe you have a sibling and you've pushed them on the swing before, then if you push your sibling on the swing at just the right time, you can make them go higher and higher and higher. That's what's happening in a microwave. Most things in our food are water-based. So microwaves are actually geared to produce the frequency of electromagnetic radiation, the frequency at which a water molecule will naturally vibrate at. We call that the natural frequency. And it just so happens that that frequency that it oscillates at happens to land within the microwave region. And we just got fortunate that it landed in something that wasn't completely detrimental to our health, like X-rays or gamma rays. But anyway, so we've invented a machine that replicates an electromagnetic wave that oscillates at the same frequency as the water molecules. And then that way, when you turn on the microwave, it's like the microwave is pushing your sibling on a swing and is giving the oscillations of these water molecules in your food higher and higher amplitude, which will make it jostle faster with more energy, which will make it warmer. So that's really cool. Another thing in the microwave region are cell phones. So there are radio towers, and for those of you who you know, do a lot of driving along the highway, you know, in Toronto we have a lot of prevalent radio stations. But if you're driving away from Toronto, let's say toward Ottawa or south toward London or what have you, eventually you will drive out of range, and you know, you've got to switch radio stations. Well, every now and then on the highway, you might see a radio tower. And the radio tower is sort of like a Wi-Fi extender. It picks up the radio signal and rebroadcasts it with a stronger amplitude. So those are radio waves and radio towers. And on those radio towers, actually, I'm going to do a really crappy, actually, you know what? Let's see, maybe, come on, maybe I can find a picture for you. Aha. Aha. I gotta find a, let's see here. Okay, so I'm not seeing a good picture of what I'm looking for. Is this it? Oh, this is sort of it. So you might see these along the highway. And this is sort of two things in one. This is not only a radio tower, it's also a microwave tower. And your cell phones work on a microwave scale. They work on like the 1 gigahertz to 8 gigahertz region. And we'll reference that back in a second. But they're killing two birds with one stone, which has always been a morbid saying. But anyway, two birds with one stone. Not only is this a radio tower to help broadcast radio signals, they also have microwave dishes on the radio tower, and that helps propagate the cell phone signal. So the radio towers are actually sort of misnamed. They're both radio and microwave towers collectively. And these little dishes here, those are the microwave dishes that are help propagating the microwave signal in addition to the radio tower. The radio tower is just an antenna. It doesn't need a dish like this. Now here, if I go back to here, I said the cell phones operate around the 8 gigahertz, well, 1 to 8 gigahertz region. Gigahertz is times 10 to the 9. Giga is times 10 to the 9 hertz. So if you look here, times 10 to the 9 is well within the microwave region. And you know, your microwave will operate somewhere up here, so still in the microwave region. But anyway, beyond the microwave region, we call it infrared. Now, infrared is wavelengths in and around, well, 10 to the minus 5, 10 to the minus 6. Humans are usually accustomed to using nanometers because those are the frequencies we can see. So this is going to be around 700 times 10 to the minus 9, which if you do that math and simplify it, it's going to be around 7 times 10 to the minus 7, right? Because 700 is 2 orders of 10. So add that onto the minus 9. So infrared is sort of below 700 nanometers. So 800 nanometers is considered infrared, very close to visible, but still considered infrared. Anything in like 10 to the minus 6, which is 10 times smaller than or 10 times smaller than red light, we consider that to be infrared. And infrared, humans can usually sense this as heat. So when you're by a campfire, and you hold your hands over the campfire, yes, the fire itself is throwing visible light through Boltzmann distributions. That's why it appears red, because it's throwing light down over here in the red region. But anyway, the heat that you feel with your hands, that's infrared heat, infrared radiation, and that literally bakes you. Also, speaking of baking you, that's also why microwaves are very dangerous for humans, because most of our bodies are water, and the microwave is specifically designed to heat and jiggle water molecules. So if a living person or animal were to be subject to a microwave, it would literally cook you from the inside out. The water in your body would be jiggled and heated up, and it would kill you pretty quick. Just to put that into context, I think the average body temperature should be around 37.5 degrees. And if you have a fever, you might spike a fever of 39 degrees. So your internal body temperature, even if it's 2 degrees warmer, is considered a health risk. You know, a fever is generally something that's bad and should be monitored, right? If your fever goes beyond 39 or 40 degrees, you should probably go to the ER, to the hospital. A microwave takes water in meat or food in the fridge. What is your fridge at? 6 degrees, 5 degrees, depending on the fridge. And it heats it up to something warm to even to your mouth or to the touch. That's probably about 40 or 50 degrees. So your microwave can take meat and heat it up from 6 degrees to 50 degrees in a minute. So if you as a human or an animal is exposed to a microwave, very deadly, very quickly, you know, in a matter of a few minutes, not even, you would feel very ill, very serious health consequences, if not death. So, you know, please be very wary of that. It's not the radiation itself that kills you. X-rays are deadly for other reasons. It's not the microwaves themselves that kill you. It's the strength of the microwaves that kill you. So you might be thinking to yourself, oh, cell phones use microwaves. Well, there's this whole debate about whether or not cell phones are good for you or cause brain cancer. They won't cause brain cancer. They might, well, for those of you, or for those of the people who are saying this, if they were slightly more educated, they wouldn't necessarily be worried about brain cancer per se. They would be worried about cooking your brain, because they operate on the microwave scale. The difference, though, is the intensity. The microwave oven that you use is, 1,500 watts. It pulls like 12 amps of current out of your wall. And, you know, the amplitude of these microwaves in your microwave is quite high, because it's specifically meant to deliver a lot of energy into the food. The amplitude of your cell phone's microwave signal is very low. So there's not a lot of energy in the wave because the amplitude is low. And really, you're not trying to draw power for your phone from the microwave signal. You're trying to just send information, communication, voice, data, what have you. And you don't need a high amplitude for that. You just need a non-zero amplitude to carry the information to the cell phone towers. So your cell phone is perfectly safe, even though it operates on the microwave scale. The amplitude is quite small, and you will not cook your brain. But that's where that sort of health concern came from with using cell phones. It was never really about brain tumors. It was about concentrating microwave radiation near your head, and presumably the worry there was that it could cook your brain. But the amplitude is far too small for that. Anyway, beyond visible light, we all know visible light actually. So let me just jump over here. So visible light, the lambda range that we're used to is in the nanometers. Nano meaning times 10 to the minus 9, but it's 400 nanometers, so it's actually times 10 to the minus 7. So it's sort of in that sort of ballpark range. But it's around 700 nanometers to 400 nanometers, or 7 times 10 to the minus 7, or 4 times 10 to the minus 7. But we usually use nanometers. And 700 nanometers is around red, 400 nanometers is around blue or violet. And the frequency range that accompanies this is, they don't even have a prefix for it. It's just 10 to the 14, or no, 10 to the 14 is still infrared. It's around 10 to the 15 is the frequency range for visible light. Beyond visible light, and I think I said this before, humans are very self-centered. We name things around what we can do and what we can't do. So visible light, infrared, infra in I guess English terminology or Latin terminology means like below red. And then ultraviolet, ultra meaning greater than or above. Ultraviolet means above violet or above blue. So the electromagnetic spectrum above visible light is called ultraviolet light. And these are things above 400 or smaller than 400 nanometers wavelength. So 300 nanometers for 200 nanometers. In terms of prefixes, that would be sort of in the 10 to the minus 7, 10 to the minus 8 range. And in terms of frequencies, you're looking at in and around sort of 10 to the 16, 10 to the 17 frequencies, hertz. And then beyond that, that's when we start getting dangerous. That's when it can start affecting our skin. So at the upper end of ultraviolet frequencies, that's how we get sunburns. Our biology is such that, we will be very negatively impacted by ultraviolet light. Clearly, there are things that are not, and there are things that thrive on ultraviolet light. Bacteria is not one of them. Bacteria is killed by ultraviolet light, but there are things that like it. And if you cross over even to higher regions, you get X-rays, and X-rays have such a high frequency that they can penetrate through most objects, like soft tissues, and that's how you can X-ray your bones. It's just light that your eyes can't see. And you go to the dentist, they can X-ray your molars and your wisdom teeth and stuff like that as well. Or if you go to the hospital because you landed on your arm, they can X-ray your arm. However, these are very harmful. It's really a numbers game. It's a statistics game. X-rays will increase your probability of cancer or radiation poisoning. And the more X-rays you have, it's a cumulative effect over your lifetime. It's a numbers game. So the more X-rays you're exposed to, the more likely it will damage some of your tissue or some of your cells and cause them to be cancerous. And that's not necessarily going to happen with one X-ray, but it's a cumulative effect. So that's why when you go to the dental office, they put that lead bib on you, because they want to X-ray your teeth and they want to sort of reduce the numbers, reduce the statistics of having the rest of your body exposed to X-rays. Now, I've always thought that funny because like they cover your body, but then they shoot X-rays right at your brain, which I've always thought was kind of funny. Like they protect your organs, but they shoot it right at your most important organ, is your brain. So kind of funny, but again, it's a numbers game. The more X-rays you get, the worse off you'll be in the future. And then gamma rays, let's hope no one experiences gamma rays. Gamma rays are sort of beyond X-rays, and they're super high powered. I think if you're familiar with the Marvel universe, gamma rays are what is cited to be responsible for creating the Hulk. Bruce Banner, I believe Dr. Bruce Banner turned into the Hulk because he was a scientist and he had an accident in the lab with gamma rays. That's not true. Gamma rays would just kill you. They're so high energy that they would just kill you. No way would you turn into the Hulk. And the frequency range there is 10 to the 20 or higher, really is what we're looking at there. And the wavelength is quite small. 10 to the minus 13 is quite small. So you see here as you're going up in the frequency, as you're going up or across the electromagnetic spectrum, you are getting smaller wavelength and larger frequencies. Okay, so that's where we're going to leave off today. We'll pick up the remainder of the curriculum tomorrow, and I think tomorrow is the last day we need to cover all of electromagnetic radiation. And whatever time we have left tomorrow and on Thursday, we can spend on exam review. And before you ask, no, I have not made your exam yet. So exam review, I guess I should really just say is course review, stuff like that. Okay, so that's it for today, guys. Thanks for coming out, and I will stop the recording now, and I will hang back and ask and answer any outstanding questions you guys may have. Ciao for now, and I'll see you guys tomorrow.